So I hope voice is clear. Okay.
Yes, sir. Voice is clear and screen is also properly visible. And I
Mm.
welcome all the participants for today's session. And Aswat sir's teaching style is amazing. Means I really appreciate the way he writes down all the things so that participants will be able to kind of think along with him. So
Thank you, sir.
I-
Thank you so much. Yeah.
okay, sir. You can start the session.
Yeah. So yeah, how many number of participants are there, sir? Right now, 216 are there. Okay, maybe 2 or 3 minutes we'll wait, sir.
Yes,
Let
sir.
the
We can wait for 2 more minutes.
two more.
Let's wait for a couple of more participants.
So, is some
Meanwhile, if participants have any particular query from previous sessions of Aswat sirs, then they can just write it down in the chat box. Sir will answer, of course, after the completion of the session, but uh, just
right.
for his knowledge, right?
Yeah, yeah.
Participants are requested to just write. And in case if you have any feedback, then also you can give. But in case of queries, especially, you can just write it down in the chat box.
Yes, yes, yes.
So now participants are more than 250, so we can start.
Yes, 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 sir. Okay, so very good afternoon to all the participants. Right, so yeah, I just checked the content being covered by Nivedita Deji for the past two sessions. So I saw the introduction of quantum computing in terms of technology was given, and also I saw the quantum information being stored as a bits, that is quantum qubits. Okay, and how the qubits were processed using quantum gates, explicit description of quantum gates in terms of quantum unitary operators, which is actually a matrices, transformation matrices, which were also given. Okay, so I, just to keep everything in the prospect, the flow, I thought I should speak to Nivedita Ji and also plan my sessions to have a continuity. Whatever I do should be in sync with she intended to do in the next couple of sessions. Okay, right? So, as per the discussion and as per the flow, to make some sense, okay, what I have thought is I'll introduce to you people something called for today Dutch algorithm. Okay, so Dutch algorithm, just a minute. Okay, just take this. Yeah, okay, it's too thick. Okay, just a minute. Okay, Dutch algorithm. Deutsch. I'm sorry. Okay, Dutch algorithm. Okay, and also I will discuss the extension of this. Actually, it's called Dutch Joyce algorithm. Okay, okay, it's Joyce algorithm. Okay, and I'll also briefly give the introduction to something called Simon's algorithm. Okay, right? And if time permits, we can even touch something called Bernstein's Bernstein Vajrani algorithm. Okay, these are all fundamental algorithms, and there is one thing called uh, Kitow's algorithm. Will not touch that because it is to be too much. Okay, so in 1 2 hour session, we can't do all those things in such fashion. Okay, right? Okay, so probably Nivedita ji might have introduced to you people some quantum circuits. Okay, right? Quantum circuits you might have introduced, and quantum. Uh, there is a possibility to quantum circuits is to do the computing in much faster fashion, right? Okay, so yeah, right. So the main advantage of quantum computing comes where? The main advantage, okay, comes from, okay, the possibility to store the information, okay, information in superposition, okay, in superposition. That is the main advantage. Okay, why it is advantage? The moment I have information written in terms of superposition, okay, here if you see the information is embedded, okay, into alpha and betas. Okay, so 2 bits of information is stored on one atom or a one qubit is a very good progress. So we can go on to increase the number of qubits, which is we can increase, okay, the qubits, number of qubits, and go on to store 2 to the power of n bit information, okay, on n qubits. Okay, that is how the quantum advantage comes. Okay, right? And one more thing is not only storing, it is also not only storing the information, it also allows us to process this much information in much quicker fashion, okay, in very quick, okay, quick way. That is where the extended advantage or the completeness of advantage comes from quantum computing. So first thing is you store the information, multiple information in one go, and process the multiple information in one go. That is why the computing time is going to be reduced if you try to do this. Okay, right? So very nice. That is a good thing to have. So now, uh, what is that? Okay, for example, let's say I have a function. Let's have a set of values. Let's say x is equal to 0, 1, 2, 3, 4, 5, 6, and so on. These are the numbers I have. Let's say consider. Okay. Now I want to find the task is to find, okay, what is f of x for all this above, for all values. Okay, fine. What I can do, let's say example, if the function is fx is x square, I'll feed all the information and find f of x values. Okay, so what is that? That would be, I will be I'll be taking x values and I will be finding f of x values and so on. Let's say something gives me something, something gives me something, and go on. I'm going to find that x and f of x values for f of x values for a given x. Now, it will take some time. It is time taking processes. It will take, okay, time taking process. Okay, and to reduce computing time, what we will do, we can do reduce the computing time, we can do parallel processing. Okay, what is that parallel processing is, provided, let's say, the one calculation doesn't influence the second calculation. In that case, I can immediately start, okay, I can immediately start doing parallel processing. Okay, so parallel processing is such an advantage. What we usually do is, okay, wait a minute. What we'll do is, we'll divide the input window into parts. Okay, let's say part 1 and part 2. I'll take each part to each computing unit or a processing unit and calculate and reduce the computing time to half. That is usually we do. So that is the user method. But if I am not still satisfied with that kind of a reduction in the computing time, I can go with the much more multiple number of processors. So that is what quad core, octa core, like different kind of a high multiple processing units which we are using these days. Okay, but in the case of quantum computing, there is a way. What is that way? In quantum computing, okay, right? Okay, there is a way. There is a way to calculate all the function values, all the f of x values in one shot, in one go. Okay, so that is actually called quantum parallelism. Quantum parallelism. Okay, so what quantum parallelism allows me is, it allows me to find all the function values, f of x values in one shot. How? We will take the x, convert the x into binary strings. For example, 000 stands for, okay, this is a binary, okay, and x is in decimal. Okay, so 0, 1, 0, 0, 1, 2 means 0, 1, 0, 3 means 0, 1, 1, so on. This table will go on. Okay, right? So, and since I'm talking in terms of quantum computing, I would say 0, 0, 0 cat, 0, 0, 1 cat, 0, 1 cat, and so on. Okay, and how do I find f of x values? I'll also find f of x values in terms of f00 get like this. Okay, so this is how there will be some kind of a function, there will be some unitary gate, unitary function. Okay, there is some kind of a block box. Okay, right, and or it can be a oracle, right, some kind of function which we don't know what is there inside. Okay, so what it takes, this function would take all the X values in terms of query registers. Let's say these are query registers. Okay, right? So it takes all the possible values of X, and it also takes something called ancilla register. Means something, some kind of a the indicator. Okay, right? So we usually have some kind of an indicator which tells me whether things are, like say, we don't need to check everything. The indicator is a one which actually tells me, okay, some kind of a litmus test. Okay, so that is the, like, litmus paper is what it does. Dip it in a liquid, it changes its color depending on the liquid what I am testing. Okay, something like a litmus paper. It's in here in this case a quantum qubit register which could be in zero state or one state. Okay, right? So let's say it is in zero state. Fine. Now all the query registers goes. There is the ancilla. Let me call it ancilla, and it spits out all the X values as it is without being disturbed. But whatever the information is there here, okay, in the ancilla register, I'll get the f of X values. Okay, right? Remember one thing here, I have so many query registers. I have only one ancillary register. It is not like that. I would also have some set of query the ancillary registers also. Okay, all of them can be put in zeros. So I'll get all the f of x values in one shot. I'll get to see all the values of f of x in one. Okay, so this is a quantum parallelism for you. Okay, so what quantum parallelism does, as if it is like you feed all the x values in one shot as a query register, or take the information of all the x values, embed them into the amplitudes of a quantum superposition state created from the qubits and feed it to the unitary function, a block box which we don't know. And beauty of that block box is it does something, it transfers the information of x onto the ancillary register, onto the ancillary register. Not just the x value it transfers, it finds out the function of f of x, function of f of x, and transfer to the classical register. That is the quantum parallelism circuit for you. Okay. Now, since we wanted to get into the quantum, we want to get into the algorithm. So we are not getting too much discussion. We'll do too much discussion on quantum parallelism. What we do, we take the conclusion or the inference from that quantum super parallelism, and will straight away will discuss Dutch algorithm. Okay, DUETSCH, that's algorithm. Okay, fine, we'll discuss that. Now, just now we just discussed quantum parallelism. Okay, what is this Dutch algorithm? Is it combines quantum parallelism, okay, parallelism with the quantum interference. Okay, it combines, and it is going to give me a very powerful, okay, implication, right, results. Okay, right, what is that is, we just saw the functional values found in one go. Okay, if I use quantum parallelism, if somebody tells me not only the function values you can find, not only function values, you can, if somebody says you can also find, let's say, a sum of function values, okay, and also some difference of some function values. Okay, basically the relations between putting the function values together or subtracting. See, in the case of quantum computing or in binary computing, binary system, addition, we use addition modulo 2. There is nothing like subtraction. Everything is addition. Why I'm saying, let's say if I have a 0, if we add 1 to it, it becomes 1. Okay? And if we have 1, you add 1 to it, it becomes 0. Okay? So if you want to subtract 1 from 1, actually 0. So no need to subtract, you can just add it. Okay? Right? So that is what we'll not bother about subtraction, we'll only bother about adding. So a quantum parallelism with the interference is going to give me the function values plus the sum of the function values of the system of the input it will give. Okay, so that is where the quantum interference, which is going to add an extra like extra effect to the quantum parallelism. Why it is called quantum interference is a very simple thing. If you get back and try to understand what double slit experiment, if you just recollect double slit experiment, okay. So what is there is, there is a light source, okay. Let's say laser source is there, okay. And now from the laser source, okay, and you take the light and use two slits, okay. So light will fall into the slit. There is a slit 1, slit 2. Slit 1 acts like its own individual source, and let's say there is a screen here, okay, right. Now since it's a coherent light source, let's say light from one source would reach like this, okay, to one point, and light from the other coherent source would reach exactly in same phase. Okay, so the, let's say, let me call the ray 1, ray 2, r1 and r2 reaches, okay, screen in phase and leads to constructive interference. Okay, right, which means there is a bright fringe is created, a bright fringe, bright light fringe. Okay, now let's go to the next point immediately after. Let's say light from one ray comes and hits there, the light from other ray comes and hits exactly in opposite phase. There I'll have a dark fringe. Okay, so this would correspond to dark fringe. Why it is dark? It is like two people are trying to pull same thing. If they are equal in strength, they are not going to move that because it is stuck in between, something like that. That ray coming from the top is trying to pull from up, and ray coming from the bottom trying to pull down. The disturbance, there's some kind of a, if there is a like some kind of a material is there, then with each energy the rays are trying to pull up or pull down. So because of that, what happens, they are not able, they are not going to be able to just a minute. I'll just see the message if there is any chat questions. Nothing. Okay, so there is a destructive interference, there is a constructive interference. So it is a quantum interference, right? At quantum level, the light energy coming and interfering and giving us the positive enhanced light, and at destructive interference, the light comes with out of phase and it couple and they destruct each other. There is a dark fringe is created. So that is what the quantum interference is. So if you see here, there is a addition of positive like out of phase or in phase signals are happening. So from there you can say, actually, so this addition of things is actually going to happen in the case of quantum parallelism as a quantum interference addition, which is going to give me the Dutch algorithm. Okay, right? Okay, so Dutch algorithm not only allows me not only allows me um, finding of function values, it also allows me to find multiple function values at a time. Plus, it allows me to find two function values and their sum in one go. Okay, right? So let's consider a simple circuit, Dutch circuit. Okay, right? Dutch algorithm circuit. Fine. So let me enlarge slightly. Okay. So this just now I told there is some kind of a black box which does the job for us. Okay. Now even the company fellow should know what is the what is that is, right. Okay. So just let me increase the thickness. Okay. So just try to understand what is that block box could be. Okay. So now as we know a C not gate. Okay. Very nice. So C not gate, if there is some zero comes as it is. If there is a one comes as it is. Because the control is zero, there is nothing is happening. Okay. Now, if control is one, okay, just a minute. If the control is one, what is going to happen? If the control is one goes as it is in the control, but target gets flipped. You see, target gets flipped in a way for the control, target value is getting added up. So that is what the flip mean. It's addition modulo. So that's why I'll have this as a zero. You can say even if the control is target is zero, okay, in that situation, I'll have 0 plus 1 giving me 1. So that is also flipping. Another option, another case. Okay. So which means a controlled NOT gate is some kind of a function which going to take the control value and that control value in the target. Okay. So what I will do, let's take that inference. Let's say in general, let's say some X register is, but X can be either 0 or 1. Okay. Now, deliberately, I'll take my ancilla, my target bit is like a litmus paper as 0. Okay. Now you say X comes as it is. What I have here? 0 plus X, which is X. Okay. Remember, it is giving us the like some kind of a implicate, some kind of a no impression. What is that? X is replicated, some kind of a cloning. Okay, but remember the X which I am putting here is a single bit state, a quantum qubit being forced to exist in a single bit state, which is 0 or 1. If I take X in superposition, I would never able to replicate that. Remember that is because of the quantum inability to replicate any quantum system exactly the same way. It is actually supported or it is actually confirmed by something called no cloning theorem. Okay, right? For the time being, if you see C not gate for a single bit input, it does that. So I can have something like we can have or we can have or there is a possibility, okay, there is a possibility to have, okay, some unitary function, okay, which takes an x value or as a control, sorry, as a control input register, okay, right, and it takes an ancilla 0, okay, right, it takes an ancilla 0, this is 0 here, and gives out x as it is. But interestingly, in the place of processed, after processing, what I get? Okay, for time being, let's say this is y. Let's say I don't know that. What is explicit form? I don't know. Okay. So there is a possibility to have y being replaced by f of x, or y getting updated by f of x addition. Just like C naught earlier, just adding x as it is, here f of a function value of that x value is going to be added. So what I'll have here, I'll have x, I'll have y plus addition modulo y plus x. Okay. Now, what I will do, if I enforce y equal to 0, implies what is going to have? I'm going to have a unitary function where x is one input. I have one input as 0. So what I'll have x as a coming out. And in another case, I'll have f of x. Okay. Just by reading what is the second register output, I can find functional values. Okay. So this is a kind of a block box or an oracle, okay, which helps me to find that function values in one shot. Okay, right? So in the case of Dutch algorithm, okay, in the case of Dutch algorithm, the circuit would slightly look in the same fashion, little bit upgraded. What is that upgraded is? The circuit would be, okay, so there will be x, there will be y. The x goes as it is, but y goes with addition modulo of f of x. Okay, this is a unitary functional gate. Okay, so there is a classical register, sorry, quantum register or a query register. Okay, so I need to have a generic x. What I will do, I'll start from 0 and take that 0 and send through Hadamard gate. I'll have a superposition of 0 and 1 with equal probability. Okay, and instead of taking ancilla bit to be 0, so I'll do one thing. I'll have even query ancilla bit also in the superposition. So I'll not have equal superposition with a positive relative phase. I'll have a negative relative phase between 0 and 1. Okay. Now, in the query register, I'll have Hadamard gate return, sorry, applied. But in the case of Ancilla, I'll not have any Hadamard. So this is the Dutch algorithm circuit. Okay. So now what happens if I have a circuit like this? Okay. It's interesting if you just see part by part, what is this initial quantum state, which is tensor product of 0 and 1. In short, I'll write as 0, 1. Okay, it is allowed. Fine. Okay. Now, the first one is 0 ket is a control, 1 ket is a target, ancilla. Now, what is happening for the psi 1, which is at this point, psi 1, this is psi 0. At psi 1, what is happening? There is a Hadamard acting on first register. There is a Hadamard acting on the second register. So simply I can write there is a superposition of positive relative phase tensor. There is a superposition of negative relative phase tensor. Okay, fine. So which means I'll a quantum output which is looking like okay, okay, so some control and some target. Okay, now so control, if you carefully see in the control, there are two terms, one is 0 bit and 1 bit. Okay, so for a given 0 bit, what is the effect on the control? Sorry, target 0, right? For a given one, what is the effect on the target? That I should know. So what I will do here, is, yeah, what I will do here is, I will first find out what is, okay, let's say first find out for a generic x, okay, for a generalized x as a control, okay, as a control, what is what is the effect of unitary function on target. What is the target? Target is 0 minus 1 divided by square root of 2. Okay, fine. I want to find that. Let me write down unitary functional or unitary gate acting on x. Okay, that control is 0 or control is x, target is superposition. Okay, fine. Now, as we know, just we saw earlier, unitary function acting on for a given x, for a given 0 as an ancilla, we just saw, right? We just saw, okay, we just saw 0 being replaced by 0 plus f of x. Let me write down. Okay, so this is equal to x acting, x would control remains as it is, but the target going to changed by f of x. Okay, that is the first input. The second input is x remain as it is, 1 replaced as f of x, addition modulo, divided by square root of 2. You should not forget. Okay. Now, if you carefully see here, I can simplify things. Okay, you add anything to 0, it is going to remain anything. Okay, right? The second case is, okay, you add 1 to anything. I can't say it can be anything because it can change. Okay, so that is very, very important. So if I just take unitary action on, okay, unitary action on x 0 minus 1 divided by square root of 2. If this is an input, I'm going to have, you can take a common, x you can take a common, I'll have f of x get minus 1 plus f of x get divided by square root of 2. Okay, right? So if you just to see, carefully see, this is what happening here. Now, let me see some scenarios where for a given x, what can happen? Let's say discussion. Okay. Let's say for a given x, I will not bother what is the x value. For a given x, if f of x is going to be 0, okay, what it implies? It implies x, the first entry is 0, okay, f of x is 0 minus 1 plus 0, okay, divided by square root of 2. Okay, so what is the result? Result is x 0 minus 1 divided by square root of 2. This is the output. Fine. Okay. What if for a given, if given x, f of x is 1. Okay, we'll not bother what is x value. Let's say for a specific x value, a function value is going to be 1. Okay, so what is that case? Okay, what is that case would be 1 plus 1 divided by square root of 2. Now you see carefully. Okay, now if you see, okay, just a minute, let me add. If you just see carefully, I'll have x here, 1 here, 0 here. Okay, 1 plus 1 is 0. So basically, if there is a 0 minus 1 ket, here 1 minus 0 ket. So depending on f of x value, the output is changing. Okay, which means there is a way I can generalize the scene, generalize or summarize. What is that summarize is, let me summarize. What is that summarize is unitary action on x, okay, unitary action on x, whenever the target is in this fashion, okay, I'll have the output. See, now I'm going to play a small trick. output would be minus 1 to the power of f of x, x cat, 0 minus 1 cat divided by square root of 2. How did I do? If f of x is 0, I'll get this output. If f of x is 1, I'll get the second output. So I clubbed both of them into one equation so that depending on the f of x value, my output is changing. So that is what I did. Now let's come back to the specific case of x. Okay. Now let's worry about the x values. Okay. What is that is, let's say if x is 0. Okay. What happens in that case? Then let me write from the top. Okay. From the top, if x is 0, I'll have 0, 0 minus 1 divided by square root of 2, okay, is equal to minus 1 to the power of f of x, 0, 0 minus 1, okay, okay, I need to write a little bit below so that I'll have, okay, is equal to, I'll have, okay, what is the output? Output is minus 1 to the power of f of x, 0, 0 minus 1 divided by square root of 2. This is a specific if x is equal to 0. If x is equal to 1, those are the only possibilities in binary system or in a quantum system. Okay. So then u of f acting on 1, 0 minus 1, okay, is equal to minus 1 to the power of f of x, 1 cat, 0 minus 1 divided by square root of 2. Okay, I'm not done anything, I just took this. If x is equal to 0, 0, this is the output. If x is equal to 1, this is the output. Okay, now I can put them together, right? That is what I want to know in the first place. What I want to know in the first place, if you go back, control is actually superposition of x being 0, x being 1. Okay, so now x being 0, what is the result? I know. X being 1, I know. So I can put them together and make the superposition. I can write what will be the effect of unitary on the superposition of x being 0 and 1 as a control on the target of 0 minus 1 ket. Okay. So this would be, right? So for x being 0, I have a result minus 1 to the power of f of x. Okay. Right. So 0. Let me write down explicitly everything. Okay. Right. I have to divide it by 1 by square root of 2 because I'm taking that square root of 2, right? So minus 1 to the power of f of x, 1 ket divided by square root of 2. I am just summing both the above two terms and then divided by square root of 2 so that I would know what would be the control effect on the target. Okay. Now let's simplify this expression. What I'll have is minus 1 to the power of f of x, 0 cat, okay, plus minus 1 to the power of f of x, 1 cat divided by square root of 2, 0 minus 1 square root of 2. This is the output. Fine. Okay. Now, very good. I know the output. Okay. So, for a given superposition input, for a given superposition target, this is the output I am getting for that unitary function or a block box. Okay. Now, let's specifically see some situation where a functional box value or a functional form is of something. What is that something is? Let's say, okay, again, if f of 0 is equal to f of 1. It is possible, by the way, because in binary system, the values are only either 0 and 1. So sometimes both values can be 0, right? So, or both values can be 1. So in that case, then, okay, right? Let write down the situation. Unitary function acting on a superposition of 0 plus 1 divided by square root of 2 as a control, 0 minus 1 divided by square root of 2 as a target is equal to, okay, minus 1 to the power of f of x, let's say, that is some value, and plus, sorry, 0, okay, plus minus 1 to the power of f of x, some value divided by square root of 2, 0 minus 1 divided by square root of 2. Now, if you see, both of them are equal, okay, which means both of them has to be either zeros or ones. Okay, let's say if, okay, and f of 0 is equal to f of 1 is equal to 0. What happens in that case? This is the entire term becomes 1, this entire term becomes 1. Okay, so what I'll have? I have just 0 minus 1 divided by square root of 2, 0 minus, sorry, 0 plus 1 square root. This is the term I'll have. Okay, fine. There is other case, other way, other possibility is also there. What is that other possibility? F of 0 is equal to f of 1 is equal to 1. What happens in that case? Which is minus 1 to the power of 1, 0 cat, minus 1 to the power of 1, 1 cat, divided by square root of 2, multiplied by 0 minus 1 square root of 2. Okay. So what is the result? Result is 0, 1 divided by square root of 2 with both minus signs. 0 minus 1 divided by square root of 2. What I do? I take the minus sign out. So inside I will have a positives. Okay. Right. So this is I'll have. Now, is there any possibility to summarize the both the scenarios of f being equal to f0 and f1 is equal to zeros and ones? Of course, possible. Okay. What is that possibility is? Unitary function acting on 0 minus 1, sorry, 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2 is equal to, okay, if you see this is there is a minus sign here. In the previous case, there is a plus sign. Okay, what I'll do, I can simply say the plus or minus 0 plus 1k divided by square root of 2, 0 minus 1 divided by square root of 2. Okay, right? What is I should say? If f of 0 is equal to f of 1. Okay, this is a generalized solution. Okay, even further I can do, what is that situation? Okay, the other scenario, other case where f of 0 is not equal to f of 1. This we have to see, right? What are the possibilities? What are the possibilities? F of 0 is 0 and f of 1 is equal to 1, or f of 0 is equal to 1 and f of 1 equal to 0. So this is the unequal situation. Okay, in this case, if you look back, this is an expression. This is an expression we have. So let me write down, for f of 0 is equal to 0, f of 1 is equal to 1 case, unitary acting on 0 minus 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2 is equal to minus 1 to the power of 0 is just 1, minus 1 to the power of, okay, let me remove that mistake, minus 1 to the power of 1 cat, divided by square root of 2, I'll have 0 minus 1 divided by square root of 2. Okay, so what is the result? Result is just a 0 minus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. Okay, let's keep this and just see another situation where f of 0 is 1, f of 1 is equal to 0. You can guess the situation here. Minus 1 to the power of 1, minus 1 to the power of 0 divided by square root of 2, 0 minus 1 divided by square root of 2 here as a target. So if you see here, the first one I'll get a minus sign, second and I'll get a plus sign. Okay. What I will do now, I'll just extract the minus sign out. Okay. So that I will have a overall minus in the sign inside. If you carefully see the outputs here, okay, both are same, only difference by the plus or minus sign. So now I can generalize this, like I can summarize into one equation. What is that one equation is? One equation is unitary function acting on 0 minus 1, sorry, 0 plus 1, 0 minus 1 is equal to plus or minus 0 minus 1 divided by square root of 2, 0 minus 1 divided by square root of 2. Okay, if f of 0 not equal to f of 1. Okay, so in this case, I got this result. Okay, so let's summarize all the cases into one simple equation. What is that? Is a function output or, okay, let me write down specifically, unitary function acting on 0 minus 0 plus 1, 0 minus 1 divided by is equal to plus or, okay, let's go back and recollect. This is a solution when both of them are equal, and this is a solution when both of them are not equal. So I should consider all the scenarios, which is going to be plus or minus 0 plus 1 divided by square root of 2, 0 minus 1 divided by square root of 2, plus or minus for f of 0 equal to f of 1. You should not forget that. 0 minus 1 divided by square root of 2, 0 minus 1 divided by square root for f of 0 not equal to f of 1. Okay, right? So that is what the, as per the quantum register, if you go back quantum circuit, after the unitary function, you will get psi of 2. The psi of 2 would look like this one. Okay, so psi, this is a psi of 2. Okay, so this is the both the possibilities are there. Okay, now what is happening now? Next, after the circuit, if after the unitary gate, okay, after the unitary gate, I am going to act Hadamard only on the control part and bring down control from some form to some form that I don't know which form it takes. So let's try to understand. Let's say, what is psi 2 I have? The psi 2 I have is this one, where psi 3 is generated by acting Hadamard and nothing on the target, only Hadamard on the control. I'll have psi of 2 acting on that. Okay. Now, if you see, Hadamard goes act on the first query part and identity goes act on the target part. Okay, as we know, Hadamard act on 0 gives me a superposition. Okay, and Hadamard acting on the superposition would going to put back the superposition into a single state 0 or 1, depending on if there is a positive relative phase or a negative relative phase between 0 and 1. Okay, so let me tell you, acting on 0 minus 1 is going to give me 1. Okay, right? So depending on the above, I'll have psi 3 is equal to Hadamard acting on the positive superposition gives me 0. Okay, remember plus or minus 1 is there. Sorry, plus or 1 minus, okay, 0 minus 1 divided by square root of 2 for f of 0 equal to f of 1. The other possibility is Hadamard acting on the 0 minus 1 kd. So which is going to give me 1 kd. 0 minus 1 divided by square root of 2 for f of 0 not equal to f of 1. Okay, fine. I have it here. Now carefully look at this scenario. Okay, what you see is in the query register, I have 0 and 1. Okay, now if you carefully see what is the sum of f of 0 plus f of 1 could be. Okay, it could be 0 or 1. There are only two possibilities. Okay, 0 happens if f of 0 is equal to f of 1. Okay, doesn't bother if it is f of 0 and f of 1 both equal to 1 or 0. I'll get the sum is 0. And if the sum is 1, which means the both of them have to be unequal. Okay, I can use that simple analogy and I generalize the above two scenarios into one summarized equation, which is going to be psi of 3 is equal to plus or minus. Carefully, if you see, this is the place of trick. Instead of 0 or 1, I will say f of 0 plus f of 1. Okay. Now, I no need to put the condition whether both of them are equal or not. As we know, if both of them are equal, I'll get the sum is equal to 0 anyway. The both of them are unequal, I'll get the sum is equal to 1 anyway. The above two scenarios were actually considered or actually covered in this final solution. And what you conclude here is now, by just going through the quantum query register part, if you go through this, by studying this, what is this query register, you can find the sum of the function values. Therefore, by analyzing the query register, we can find f of 0 plus f of 1. That is sum of two function values. Okay. Not only that, you can extend this circuit for a very, very large number of query registers, very large number of target registers, and generalize, and you can get and the sum of all the function values in one shot. Okay, so this is a proof of a Dutch algorithm. If you have uh, if you have anything to ask, please do ask. I can repeat. Okay, right? So that somebody was asking, sir, please revise the entire thing briefly again. Okay, okay, Gauriji, definitely I can do that for you. Okay, right? So entire thing I'm going to summarize it in one shot. Okay, as we know, computing is going to give you the advantage because of one very important property, which is superposition. Superposition allows you to put all the information into one quantum state and analyze the entire quantum state in one shot. It is just like if there is a classroom, all the students are asking the questions to you. In real world scenario, classical world scenario, I'll be unable to speak to all the people in one shot because I can't analyze their question in one shot. So if I have a quantum device or quantum computer based robot, what it does, it takes all the questions in one quantum superposition state and analyze them and reply back the information or the answer to all the questions in one shot. That is what the quantum advantage is. Okay, so taken a page from there, quantum advantage could be used to embed all the argument values of a function, some x values, feed it to a quantum computer or a quantum algorithm. You can find all the function values in one shot. Okay, so how it is possible? there is something like a block box, some unitary function is there which does job for me, and like some person creates some kind of a oracle does for me, and the question is who manufactures it, who does that, is actually based on a simple idea. Okay, we just discussed that simple idea. Let's say take a C0 gate. C0 gate does that by addition modulo operation. Okay, so just something like a unitary controlled not gate, there exists some unitary controlled unitary gate which does, instead of just adding a function value to the ancilla, it adds adding the actual value of the x value to the ancilla, a function value of x is being added. If the function value is added, so then my job is done. Okay, so that is what the block box is. So Dutch algorithm is a something of that kind of a block box. Only difference here is in the control and also in the target we will use a Hadamard gate, and in the control we have uh, a Hadamard gate even after the unitary function. If such a Dutch algorithm circuit is taken or any circuit is taken, this circuit is going to give me not only the function values, it also gives me the sum of the function values. So if somebody tells you, I will give you function values and also I will give you the possible sum of the function values, is a one extra bonus, right? So we will take it. That is what. So the circuits would look like, you divide the circuit into parts, let's say layer by layer, try to find out what is this quantum state processing is all about. So initial quantum state is just a 0 ket and 1 ket. Control is 0 and target is 1. I want to put the control into superposition, target also into superposition. I'll do that. I'll have a quantum state of plus ket and a minus ket. Okay. You remember control is a plus ket and the target is a minus ket. Okay. Now a control is a superposition, target is a superposition. To understand the processing, let's say take control is some fixed state, either 0 or 1. I'll take in the form of x and try to analyze. Okay, so what I'll conclude here is if some x is there, its function values is actually transferred to the ancilla bit. Okay, so here the ancilla bit is in superposition. I'll have the function values actually transferred to the bits of superposition. Wherever there is a 0, I'll have f of x. Wherever there is a 1, I'll add f of x value to that 1 in additional modulo 2 form. Okay, now I'll start assessing what could be the functional form. Could be, if the functional form is 0, I'll have one kind of output. If the functional form is 1, I'll have one kind of output. I want to generalize for any x value. Okay, I'll write unitary function as a minus 1 to the power of f of x for any f of x. Okay, so for any x of f of x I know, at the same time I have to find for any x value. So let's say for x value is equal to 0, what would be the output? I see interestingly for x value is equal to, I'll have something, for x is equal to y value, I'll have something. I can put them together as a superposition and I'll get for a given control, the superposition as a control, what would be the effect on the superposition of target? I can interestingly, I see there is a function as a minus 1 to the power of f of x. Okay, right? So now a functional f of x value either can be 0 or 1. Let's say both the function values are zeros or 1. In that case, what happens? I can generalize, I summarize that entire scenario into one equation like this. Okay, and there is other case also. What is that other case? The function values cannot be same; they are different. In that case, how those can be different is two ways they can be different. In those two cases, if you analyze and generalize or summarize the scenario into one equation, I'll have something like this. Okay. Now put all the four scenarios into one simple equation, which would look like this. When the function values are 0 and equal, or function values is 1 equal, and the function values are unequal, I have a second option. Okay. Now, as per the as per the Dutch circuit, I'll have I'll have written. Okay, I have written. Just a minute, I forgot to connect my charger. Hello? Yeah, yeah. Just a minute. I forgot to connect my. Hello? Yeah, I hope you can hear me. Yeah. Okay, then. Okay, let me get back to the notes. Okay, right. Yeah. So before I switch on my system, I hope you can see my screen. Okay, right. My tab is there. Okay. So this is what Dutch algorithm does for us. It is going to give me not only function, it also gives me a sum of the function values. That is a very handy thing. And we will go on to see something called the Dutch Joyce algorithm in the second half. Okay. And if there is any doubt, I'll take during this 5-minute break. So we'll start the class again, our session again at 4:13 or 4:14. Okay. So let's take a break. Yeah. Okay. So somebody was asking a question. All right. So let me see. Shall we follow the same for other target also? Yeah, I think we can extend generalize for any scenario, right? Okay. Is this understand how the ready-made algorithm works, right? Yeah, I think so. Can we use it directly? Yeah, we can use. So in fact, there is no specific immediate application of this yet, but in fact, this led to the advanced algorithms. Okay. So in a way, it's paved a path for new advanced algorithms. Okay. Right. Yeah, final conclusion, as somebody was asking, the final conclusion is the Dutch algorithm would allow me to find not only the function values, also the sum of the function values in one shot. Okay. Just by finding the output of the first qubit only. Yeah, here if you see, just by studying the first qubit output, we will going to find the functional sum. Yeah. Right. I think somebody was asking a question. I think Urga Babu, if you know the desired output, what is the advantage of quantum parallelism? So it would look like not much effective when I have a very small number of bits going in and coming out, and we analyze in the simple scenario. If you go for a very, very large system, large data, in that case, this is going to have a tremendous impact. Okay, right? Yeah. So when to use this algorithm? Suppose if I want to find the multiple functional values in one go, not only functional values, I want to find the sum of functional values. In that case, it is required. Okay, right? So basically, it is doing multitasking. Okay, so yeah, for example, Grover's algorithm, there unstructured data is there. You can find an element from unstructured data in much quicker fashion. There, finding element could be converted into finding a multifunctional values, and also finding some of the functional values. In a way, it lead us to find that required element in much quicker fashion. I don't want to do the extra iteration, so I will just use the calculated functional values and sum them up, and I'll get some. You can come up with your new you can come up with your new algorithm. Okay, so which will be a tweaked version of this circuit. You can do a little bit of tweaking and come up with a new algorithm which does some extra thing. Okay, extra flavor it adds, so that would be a very perfect thing. Okay, right. So without wasting any more time, okay, so let's start next algorithm, which is Dutch choice algorithm. Okay. So having understood Dutch algorithm, we can easily go through, okay, Dutch choice algorithm. Okay. So what is this algorithm is? It is again something to do with the functional values only, but in a different way. What is that is? Okay. So let's understand this is some kind of a game that would be easier to understand. Okay. So let's say I have a set of functional values, argument values, x values. Interestingly, this time, the f of x I take, but if I have two qubits, Okay, 1 minute. I just lost the presentation. Okay, what happened? Okay, where is that option? Presentation option is somehow disappeared. Present the screen. Share screen. Start. Enter. Okay. Start. Okay, it has come. Okay, right. So the X is a single qubit information. If X becomes a 2-qubit information, I'll have 0 and 1 tensor square. In that case also, remember f of x is again 0 and 1 only. Okay, right? The function values can only be 0 and 1 if that is the situation. Okay, right? So irrespective of whatever is the x argument values, function values can only be 0 and 1. Remember that. Okay. Now, if such a thing is there, okay, for example, I have, let me write down in a regular way, not in a binary way. Let's say I have a 0, the function value is 0. Let's say I have a 1, again function value is 0, and so on. Let's say up to 4, the function value is 0. Okay, after 5, it starts giving 1. Okay, 9, it gives 1. Okay, so 2, 3, I have 0, 0. 6, 7, 8, I have 0, 0. Sorry, I have 1, 1, 1, 1. So what you see here, I have 5, like for input, first half of the input, I'll have 0. Second half of the input, I have 1. Okay. So this is the kind of a function. It's like half zeros, half 1. You can call, if this is a scenario, this function you can call it's a balanced function. Okay. Remember the x values which I feed it from 0 to 4 giving 0, x values feeding from 5 to 9 giving 0, 1 is a balanced function. I can have the inputs moved other way around. Even in that case, I will have a balanced scenario. Okay. And there is a situation. What is that situation is? Let's say I have x values. For any x values, for any x, I am going to get zeros. Or for any x, anywhere, I am going to get 1. Okay. So if that kind of a situation is there, that's gate is like that kind of a scenario, the function is going to be called as, that function is going to be called as a constant function. So f of x is a constant function. Okay. So a given f of x can be either balanced, okay, either balanced, or it could be a constant. Okay. Now the question is, let's say somebody is using a balanced or a constant. Let's say f of x could be, it could be a constant or a balanced. In the case of balanced, what I mean is it will have for half 0 for half inputs and 1 for other half inputs. Okay, right? So this is the function I have. This is for all x. Okay, right? So for all x, it is going to be zeros or 1. So, okay, now this is a kind of function somebody is using. Now, okay, the task is to find the functional nature or function f of x nature by asking less number of queries. Okay, right? What I mean is, If I want to find whether the function is balanced or not, I have to calculate f of x values, right? For a given input, I have to calculate. Now, so as usual in computing, I want to reduce the computing time. I don't want to waste too much time. So I have to find f of x nature by computing as less number of iterations or as less number of attempts and as less number of queries I would be asking to the person who is using that function. So now the game which we will be playing is, let's say Alice is there, Bob is there. Okay, Bob uses the function, that f of x function. Alice supplies x values to Bob. Now Alice has to find out to find f of x nature. Okay, she supplies x value. Bob returns f of x value. Okay, so with one query, one iteration is done. Again, Alice supplies x value, Bob returns returns f of x value. Luckily, with these iterations, let's say Alice sends some x1, Bob returns 0, Alice sends some x2, Bob returns 1. Okay, so what it means, in just two iterations, okay, Alice finds that f of x is a balanced function, because you see, if the function like gets 0 and 1, okay, uh, if functions have 0 and 1 values, there is no need to study remaining input values and what is the function values. You can simply say it is a balance. But if it is not her day, okay, if it is not her day, what happens in this particular situation? Alice supplies x is equal to 0. F of Bob would give returns 0. Alice would again supplies 1. Bob returns 0. Okay. So this iteration, if you see, if it is 2 is gone, 0 is coming out. 2 is supplied, 3 is supplied, 0 comes out. Okay. Right. And 4 is supplied, again 0 comes out. You see how many iterations? Number 1, number 2, number 3, number 4, okay, number 5. 5 iterations are taken, consumed. Still, she is not able to find the function is balanced or not, because the fifth one is going to decide. Sorry, sixth one is going to decide. What is that is, if sixth one, if she sends the number 5 argument value, if Bob gives replies 0, what it means? Sorry, what it means, the function is actually a constant, which implies a constant, because no need to see the other cases. Or if for a given 5 Bob returns 1, which implies it's a balanced function, because for the next 4 inputs it has to become 1. So if you carefully see here, it requires, if there is a 9 input values, how many were required? So 9 by 2 plus 1 attempts were required to find the function is balanced or not. Okay, strictly I need this many, either this or less. If it is a good day, it can be just 2 attempts. If it is a bad day, this is a, okay, so let me generalize that. So 2 to the power of n is the number of qubits I would be using, n qubits I would be using. I'll have a data size fed onto the n qubits in the form of 2 to the power of n. So I would be needing this many number of attempts to find, to recognize the function is balanced or not. Okay. And what Dutch Joyce's algorithm says is, okay, okay. So if if we use a unitary function just like we used for Dutch algorithm, okay, and unitary function feed all x values as x to the gate as quantum qubits, then we can find, okay, where then we can find then we can find the function nature in one shot. Okay, that is very powerful thing to say. Just in one shot you can find. Okay, so not in two shots, that is the least required for classical computing. And using quantum computing, you can do it in one shot. How it is possible is, again, the quantum unitary circuit, what we saw earlier. Okay, so the Joyce algorithm circuit would slightly look the same way as a Dutch algorithm, and there is a small difference. What is the difference? Let me show you here. Okay, right? So we'll have same unitary gate u of f. It takes x, takes y, gives x as it is, and gives y with addition model of f of x. Okay, right? That we know. Now, what we do is, since we want to feed large number of input values, what I'll do, I'll take a Hadamard's. How many? I will take n Hadamard's. I'll take n zeros. Okay, right? So simple. And then I'll have one Hadamard acting on one ket as an ancilla. Okay, so for the target control, I'll have written n Hadamards again after the processing, and I'll take the information out and I'll process and see what is the output here. Okay, just like a previous case, I'll have n query registers here and n Hadamard's acting on n query registers. Now, if you divide the circuit into layers by layers, what I'll have is, I'll have, let's say, psi naught, psi 1, okay, psi 2, and psi 3. Okay, for a generalized scenario we just saw earlier. Okay, so for the time being, let's say, for the time being, let's take a scenario where n equal to 2. N equal to 2. N equal to 2 means the two input registers, query registers will be there, two Hadamards will be there. Okay. So what is the output would look like? There is a superposition here. There is a superposition here. Okay. If you carefully see, the output at this point is, I am going to have equal superposition of all the scenarios of a 2-qubit system, just like square root of 2 square. It is just like a two quantum coins tossed together. Okay. Now, I just want to write in most generic form so that I can process it. Okay. So I will say now this is equal to, if you carefully see, okay, right, this is equal to summation over x. Remember, x belongs to 0 comma 1 tensor square, and x divided by square root of 2 square. Okay, I can send. Okay, so this one is 2 and this one is also 2. Okay, right? So this is the generalized form of, okay, generalized form of query register would look like query register, two query registers. There is two Hadamards acting on the query register, so which is psi 1. Okay, so from psi naught I have a psi 1. Okay, fine. Now let me write down. Okay, I'm sorry. Okay, so I have to take ancilla also. I have not taken here. Let me remove that. Okay, yeah. Fine. So now I want to write along with the ancilla, what is the psi 1? Psi 1 is, okay, the above one, x belongs to 0, comma 1, tensor square, 0, x 2 square, okay, and I have a 0 minus 1 divided by square root of 2 as an answer. You see, only 0 is there, Hadamad is there. That is only there. Okay, right? Now, the psi 1 going through unitary function will going to have some effect on the target based on the control values. Okay, what is that? The psi 2 would be minus 1 to the power of f of x. Control remains as it is, 2 square. Okay, but the target is going to be coming with minus sign, minus 1 to the power of f of x whenever it is 0 and 1. Okay, so that inside minus 1 to the power of f of x inside, minus 1 to the power of f of x inside, for 1 ket and 0 ket would be extracted out. So this is what my psi 2 would look like. Okay, when n equal to 2. If you want, for n equal to generic n, you can write psi of 2 is minus 1 to the power of f of x. Okay, I'm sorry, you should not forget the summation, guys. Okay, summation. Okay, summation over x minus 1 to the power of f of x minus x divided by 2 to the power of n. Okay, where x belongs to 0, comma 1 tensor n. Very important. And this one is 0 minus 1 divided by square root of 2. Okay, generic case. Okay, target bit is 0 or 1. Okay, target bit is in both superposition, right? Okay, okay, so somebody was asking fifth time is 1 but sixth time is 0, then what we can say there? Remember, the function they have chosen is, 1 minute, the function they have chosen is either balanced or a constant function. Means if it is till fifth time all once, but the sixth time it is 0, okay, means it has to be a balanced function. Okay, you should talk about the seventh time. Seventh time, it cannot have anything other than 0 because it's a function is balanced. There are only two kinds of functions are allowed to be chosen to Bob. Bob either can choose a constant or a balance. He can't choose a function which gives a function which gives sometimes 0. For 2 cases it gives 0, for 8 cases it's 1. It's not that is not a balanced function or a constant function, it is something else. So that kind of a function is not allowed to be chosen by Bob. So Bob will strictly tell Bob, you choose either balanced or a constant function, and I'll ask you a questions to you. Based on the questions I'll guess what kind of a function you are using. There are two chances only there. Two choices are there for Bob. I'll guess. So initially for two queries I can get luckily, but if not, I am going to have at least 6 attempts in the case of 10 input argument cases. Okay. Yeah. Right. Where is the end? I will see. Yeah, this is where generic n. Okay, for a generic n is there. Now always we'll keep it for a simpler case. Okay, for n equal to 2 case, let's say we'll keep it for n equal to 2 case. What is a unit reaction? We just know what is a unit reaction. Now, okay, let's try to analyze. Okay, what I mean is when psi 1 is there, it becomes psi 2, and then we need to do what is a psi 3. Sorry, what is as per my circuit, let's say I want to find what is psi 2. Okay, what is psi 2? Oh, sorry, psi 2 I found. The next thing is what is psi 3. Okay, so for psi 3, I have an action of Hadamard. Okay, if the square registers are 2, there are 2 Hadamards. Okay, so we will have a small game played here. Okay, what is that game is? Let's say I have Hadamard acting on 0 x. Okay, if x is 0, okay, in that case, what I'll get, which implies H acting on 0 gives me a superposition. Very good. If X is 1k, I'll get minus, sorry, 1. I'll get, okay, let me remove cleanly, I'll write down. This is very important. Gives me 0 minus 1 divided by square root of 2. Okay. If you carefully see, there are two scenarios. I can simplify this as some z belongs to 0 comma 1 minus 1 to the power of z cat divided by square root of 2. Okay, right? So what I mean is whenever z is equal to 0, okay, I'll not have a minus sign coming into the picture. Okay, whenever z is equal to 1, in that case, I'll get a minus sign into the picture. Okay, fine. So, fine. So, this is for the second case. For the first case, I'll have z belongs to either 0 comma 1 minus zk divided by square root of 2. Okay. The second case I have, the first case I have. Is there any way I can simplify this into one simple equation? What is that is, if you see, H acting on X is equal to summation over minus 1 to the power of X into Z cat divided by square root of 2, where, okay, where Z is just belongs to 0 comma 1. You see now, whenever x is equal to 0, I am covering the first situation. Whenever x is equal to 1, I am covering the second situation. Everything is now simplified into one generic equation. Okay. Now, this is for n equal to 1. Okay. For n equal to 2, what I'll have? I'll have h acting on 1x, h acting on another x. Okay, let me put x as 1 and 2. What I mean is there are two x values. One x value is something, another x value is something. So I've just given a different argument as x1 and x2. Okay, what I mean is x1 and x2 together can be 0, 0, 0, 1, 1, 0, 1, 1. Okay, right? Okay, so in this case, I'll write down Hadamard tensor square acting on x1 and x2 would be equal to, what is the case here? First one gives me summation over z1 minus 1 to the power of x1 multiplied by z1 cat divided by square root of 2, okay, multiplied by z2 belongs to some 0 1, belongs to 0 1, okay, minus 1 to the power of x2 into z2 divided by square root of 2. Okay, very important. I will have here Okay, what I'll have here is minus summation over. Okay, let me write down into two summations for simplicity. Z1 and Z2 both are belongs to 0 comma 1 kind of values, minus 1 to the power of x1 z1 plus x2 z2 z1 kit z2 kit. Okay, 2 to the power of 2 square root. Okay, now I can generalize into n Hadamard's x1, x2, so on, xn is equal to summation of z1, z2, and so on up to zn's minus 1 to the power of. This time I know x1 multiplied into x2, x1, z1, x2 multiplied into z2. So what I'll do, I'll write as a x dot z. Let's say I'll put as a bar on the top. What I mean is some kind of a vector, inner product or a dot product. I'll have here I'll have Z1, Z2, Zn divided by 2 to the power of n. Okay. So I just generalized what would be the effect of Hadamard acting on, okay, the query register after the unitary function. Okay. Right. So which means I have to I am able to find what is the psi 3. What is the psi 3 when Hadamards are acted on the query part. So a generic scenario is very difficult to understand. What I'll do, let's simplify it to n equal to 1 and n equal to 2, and then we'll generalize. Okay, right? So let's do that. Okay. Let's take this, a generic situation, sorry, n equal to 2 case, n equal to 2, I'll have x1, I have x2 is equal to z1, z2 minus 1 to the power of x1, z1 plus x2, z2, z1, z2, 2 square. Okay. Right now, this is what I have. Okay. Right. Okay, what is this function would be? This function would be, okay, this function would be psi 3, right? If I add the ancilla bit form, okay, the psi 3 would be, carefully if I write down, ancilla has having a function value of x there, so I'll have z, okay, I'll have x minus 1 to the power of f of x plus x dot z. Remember x dot z in the here, and there is a function 2 to the power of square coming and 2 to the power of square coming from this query and the target. Okay, so minus 1 to the power of f of x is coming from unitary effect. Okay, I'll have z1, z2. Okay, right? So yeah, just a minute. Oh, did I miss something? Where is that? Yeah, here you see. So this part minus 1 to the power of f of x, and this part is also there, and there is a sum is also there. So all those things we have to take into consideration, and I'll have psi 3 looks like this. Okay, right? Okay, so let's explicitly write for n equal to 2 case, or yeah, n equal to 2 case. So let me remove here and write explicitly. This I'll have, okay. What I'll have is 2 to the power of 2, okay, right? I'll have z here. I have 0 minus 1 divided by square root of 2. This is what I'll have for explicit case. Remember 2 qubits are there, I'll have 2, and square root of 2 square, and square root of 2 square comes from unitary function. So 2 square roots I'll have, square root of, sorry, 2 square I'll have, okay. And z could be 0, okay. So this all possibilities are there. For example, n equal to 2 case, what is the z would look like? 0, 0, 0, 1, 1, 0, 1, 1. Okay. These are the possibilities I can have. Now, one trick I can use is, what is that is, you carefully see the amplitude multiplying to z is, what is that? Minus 1 to the power of f of x plus x into z. That is being multiplying into the amplitude of query register z. Okay. Now, this is divided by 2 to the power of 2 square is there. Let's say it is there. Okay, this is the amplitude. Amplitude of z. Query register. Okay, that is what Alice receives. That is what Alice understands and try to study that. Okay, for example, take z equal to 0, 0. Okay, in that case, x dot z is obviously going to be 0. Okay, right? So what is the implication? Implication is actually comes from minus 1 to the power of f of x by 2 square. Okay, so this is the dictating factor of the amplitude of 0, 0 ket. Now, if you study this amplitude carefully, okay, for example, okay, if f of x is a constant function, okay, if f of x is a constant function, means f of 0, 0, f of 0, 1, f of 1, 0, f of 1, 1, all of them are either 0 or 1s. If all of them are 0, okay, what would be the amplitude? Amplitude is, there is a summation is there, summation over x. There is a summation over x is there, okay, right? If all of them are 0, summation over x minus 1 to the power of, okay, right, f of 0, 0. Okay, let me remove the summation, explicitly write down minus 1 to the power of f of 0, 1 plus minus 1 to the power of f of 1, 0 minus 1 to the power of f of 1, 1 divided by 4. Okay. Now, if all of them are zeros, all the function values are 0. Okay. Okay. All the function values are 0. What I'll have? 1 plus 1 plus 1 plus 1 divided by 4, which is 1. What it implies is, okay, what it implies is all the function values are 0 means I am getting 1. If all the function values are 1, in that case I'll have minus 1, minus 1, minus 1, minus 1 divided by 4, which is going to be minus 1. Okay. So amplitude coming minus plus 1 doesn't matter. What matters is the probability. What is the probability? Probability is positive square root of amplitude. It is going to be 1. Doesn't matter. So therefore, if f of x is constant, which implies z has to be 0, 0. Other way around, if z is 0, 0 implies f of x is constant. Okay. And if you just take any other scenario, let's take f of x, z is 0 and 1. In this case, let's say, try to understand. What is in this case? F is equal to 0 and 1. Okay. X minus 1 to the power of x into z is going to be play a role x1 because, okay, sorry, x2, because minus 1 to the power of x1 z1 plus x2 z2, where z1 is 0, z2 is 1, I am going to get this, okay, x2 value, the minus 1 to the power of x2. Okay, right? So one conclusion you can draw is, if you analyze query register, okay, if it falls to 0 and 0, you can straight away conclude function is constant. If not, the function is balanced. Any other values you get, if x is, sorry, z is either 0 1 or 1 0 or 1 1, if you get that state, which implies the function is a balanced. Okay, you can cross check how it is a balanced scenario. Okay, right? So let me give one scenario where a balanced relation is there. Let's say balanced means what? Balanced scenario, balanced case, where let's say f of 0 0, f of 0 1 is equal to 0, f of 1 0 equal to 1, f of 1 equal to 1. Okay, this is the case. Now I don't know what is the z. Let's say I don't know. Let's say don't know. Okay, let's say we don't know. Let's say I have a, like Bob has used a balanced function. In that case, what is the amplitude multiplying to z? Which is minus 1 to the power of f of x plus x dot z. Okay, this is the query register. Okay, this is what he has. Okay, now let's try to analyze from the above case. From the above case, I have minus 1 to the power of, okay, f of x. In some scenario I have zeros, plus whenever z is both zeros, x is not going to play, I'll have a z 0. Okay, now minus 1 to the power of, again function value is 0. Okay, this time I'll have x2 z2 plus minus 1 to the power of, okay, 1 0, right? I'll have x1 z1. Z1 is 0 by the way, 0 1 by the way, 1 by the way. So I can just remove that. Okay, plus minus 1 to the power of x1 z1 plus x2 z2, both will come. Okay, 4, right? So now if you say, if the function is balanced, so the role of x1 and x2 is going to make a lot of difference. Okay, right? Now, as we know, right? So as we know, if z1, z2 both are equal to 1 1, okay, what I have here is, right? What I have here is minus 1 to the power of x1 plus x2. Okay, right? 1 x1 plus x2. Now, for x1 for x2, if z is equal to 1 1 means x1 and x2 has to be also goes to 0. Sorry, go x1 plus x also goes to 1. So in a way, what I'm going to get is minus 1 plus 1 plus 1. Okay, so this is going to give me 0 when f is balanced. Okay, so if any other z value other than 0 0 if I get, so you can straight away conclude function is balanced. Okay, so one simple trick you are going to use is, okay, go to the circuit. One simple trick is, if the output is having z is having 0 0, straight away you conclude function is constant. You don't bother if it is not 0 0, it is anything else, you can straight away say it is a balanced function. Okay, right? So yeah, so the discontinuity, I think, okay. So let me summarize and put it to some kind of a summary. A summary. Okay, what I mean is, okay. So if there is this, if the query register is falling into 0 0 form, okay, then f of x is constant. Otherwise, in the sense, z can be 0 1 or 1 0 or 1 1. In that case, f of x is going to be a balanced. So you are only worried about whether my output is 0 0 or anything else. If it is 0 0, you can straight away conclude the constant. If it is anything else, it is going to be 0 0. Okay, right? So that is a most important thing you should conclude or remember. Okay. Yeah. So IBM textbook online available. Yeah, it is available. I think they discontinued the old version, the textbook which deals with the old version. But all those notebooks and all are available on the net. As somebody else's are actually stored it as their in their GitHub, so you can download and see. Okay. So in today's couple of sessions, what was discussed is, I've discussed the Dutch algorithm and Dutch choice algorithm. So in fact, I thought we could go to something called Simon's algorithm. Okay, right? It is not possible in such short time. So what Simon's algorithm is again it's a playing a game. Let's say there is a function which takes one value, gives some output. It gives another value, gives some output. Let's say for two inputs, it gives the same output. Okay, right? It's just like a Dutch choice algorithm, right? So obvious solution is both x1 and x2 is equal to 0. If x1 and x2 both are different, if x1 is not equal to x2, which is x2 is, let's say, x1 plus some value b, okay, right? Some value b, in that case, if the function values are going to be the same, the question is, what is b? Okay, again, to find b, you have to do a kind of a play, kind of a game. So if you play like a game, classical computing requires about let's say the order is very big. It's like if I have the number of registers, depending on the number of registers, it's like 2 to the power of n by 2 attempts would be required. But if we use, okay, if you are going to use a quantum computing, it is going to be reduced into a much smaller, that would be order of just n. to quantum computing or quantum circuits. Okay, right? So again, tremendous improvement in the computing. That is what the Simon's algorithm is. So just like we understood the Dutch Joyce and Dutch algorithm, the same way you can understand Simon's algorithm. So since the time is not there, probably Nivedita ji is going to discuss the Dutch as a Simon's algorithm, and the extension of that would be something called a Bernstein's Vajrani algorithm. So these are like fundamental algorithms one has to understand and go further for applied algorithms. Okay, I'll just stop here. Yeah, looks like there is no more questions. Yeah, Qiskit books are still available. You no need to scan, I think. PDFs are available in the net. You can just download. Okay. So I just discussed Dutch algorithm, Dutch Swiss algorithm, Simon's algorithm. A brief intro was given. Buster's Vajran algorithm. Again, it's some kind of a extension of Simon where I did not discuss. So sometime later, I think it will be discussed. Okay. Right. I'll be sharing my notes, which detailedly explains everything. And if you can go through, and you will understand that if you have not followed till now. Okay. I'll stop at this point. Hand it over to Jadeja sir, Mahipal Jadeja.
Thank you. Thank you so much, sir, for the wonderful session.
Thank you, sir.
In case of any questions, participants can ask. We'll wait for 5 more minutes
Yeah.
before.
So there is a question here by Dandigamas G. Uh, are we going to measure the first two qubits if the probability of getting one is it function otherwise balance? Yeah, you are perfectly summarized everything. Yes, that is the summary I mean. Okay, right? I just gave in a statements. You had put it the right way. Okay. Okay. Where is that? Yeah, here I have. So I have, let's say I'll have some kind of a block box. Okay. I'll feed all my queries. Okay. And there is an answer I'll keep. So there is a unitary function. Okay. Bob will calculate. This is a Bob will do some unitary operation and Bob will generate the output. Okay. The output is supplies to Alice. Okay. This is Alice end. This is a Bob send. So Bob will gives the output to Alice. What Alice does is Alice analyzes, okay, Alice analyzes the overall output state, but she only worries about what is there, okay, what is there in the query part. Okay, in the query part, if it is happen to be all zeros, boom, she will conclude f of x is a constant. If anything other than this, anything other, which implies f of x is balanced. Okay, and you said if this is coming means this will come with a probability 1. Okay, if this is not there means the probability of all zero states is 0. It is actually distributed. The probability is distributed somewhere else. That's why the function is balanced. Okay, fine. Yeah, I will be sharing Bernstein's Vajrani algorithm, the PPT, and also Simon's algorithm PPT. Or Simon's algorithm probably Madam will discuss. So I'll not touch that. But it's very interesting and the extension of Dutch algorithm. You people can go through. Okay. Yeah. I think no more questions, sir. Kripal, sir.
Yes, all the participants were very happy, and I feel that they have understood the lecture properly. Thank you so much, sir. And participants are requested to go through the notes one more time, and also they can revisit the recordings from YouTube in case if they require. Thank you. Thank you so much, sir.
Yes, sir. Thank you, sir. Thank you.
Thank you, sir. Thank you,
Anish,
Ashwat
sir,
sir and
do you
Maple
want to
sir.
add something? Sure. Yes, sir. Yes, sir. Go on. Yeah.
Hello.
Yes, Anish, sir, do you want to
Yes,
add
sir.
something?
Thank you, Ashwat sir and Maple sir. I request all the participants to complete the quiz. 2 is now open. You can finish by maybe tomorrow, sir.
No, the time was today itself by 11:59 p.m.
Okay,
That's the
that's fine, sir.
deadline. So
That's fine.
participants are requested to complete it as soon as possible. And once you start, you will get exactly 30 minutes for completion.
Yes, sir. Thank you, sir. Thank you. Thank you
Thank
very
you.
much.
Thank you so much. Thank you.
Yeah, I'll upload the notes